So there's a long history of philosophical discussion of causation, and an especially revealing discussion that has been carried on within the philosophy of science in the wake of Russell's 1913 paper. In that paper, Russell argued that causation is a folk notion that has no place in science. In a very famous quote, "The law of causality, I believe, like much that passes muster among philosophers, is a relic of a bygone age, surviving, like the monarchy, only because it is erroneously supposed to do no harm." Now, Russell argued that the closest thing in physics, and he had in mind, the Newtonian worldview, to causal relations are dynamical laws. But dynamical laws are differential equations that relate global states of the universe at one time to its global state at another. They don't describe local relations between particular events. They have no intrinsic temporal direction, and they have no exceptions. Causes, by contrast, are asymmetric relations between localizable events. For example, the striking of a match and the appearance of a flame, the baseball hitting a window and the shattering of the glass. They're more informative than global dynamical relations about what occurs on the local scale, but they depend on background conditions and they're full of exceptions. Now, the difference between these two notions is so great that Russell was recommending that we do away with the notion of cause altogether, at least in scientific contexts, as part of our official ontology, and replace it with that of a dynamical law. Cartwright, in an influential criticism, which was entirely right, and it's widely accepted, was widely sort of received almost immediately as being correct, responded that dynamical laws cannot play the role of causal relations in science and in everyday practical reasoning, because specifically causal information is needed to distinguish effective from ineffective strategies for bringing about ends. So, for example, it might be true that as a matter of physical law, because smoking causes bad breath, that there's a strong positive correlation between bad breath and cancer. But it's not true that bad breath causes cancer, and hence it's not true that treating bad breath is an effective strategy for bringing about cancer. And that difference, the difference between being correlated with cancer and being a way of bringing it about, is not one that can be drawn by looking only at the dynamical laws. If one wants to avoid getting cancer, one has to know not simply what cancer is correlated with, but what causes it, what brings it about. And the claim is that's not a distinction that can be drawn just by looking at the dynamical laws. Now, this is sort of part of history now, but there are a number of different reactions that one might have to the situation. Attempts to analyze causation, not just in dynamical terms, but bringing in something else have been tried. So probabilistic, counterfactual, and dispositional analyses are still popular. There are views that link causal relations to human manipulability, but these were thought by many to be sort of objectively imprecise and anthropomorphic. But in the last 10 years or so, interventionism has emerged, I think, as an important and clear forerunner in the discussion. It captures what was right with counterfactual and manipulability views while formalizing a scientifically useful notion. It's not without difficulties, but I think it pretty clearly captures the core of the pre-theoretic concept and provides us with the right formal framework for representing causal structure in science. Interventionism does not aim to reduce causal structure or to define it in non-causal terms. It aims for elucidation, clarifying the logic and epistemology of causal claims, telling us how to recognize causal structure and construct causal models. Dynamical equations tell us how the state of the universe at one time depends on its state at another. And this means that if we start with information about the past in the form of a probability distribution over global time slices, over past events, we can derive probabilities for events to come from the dynamical equations. The only strict relations of covariation, however, are relations among global time slices. But when we look at how the laws transform probability distribution, we find a rich pattern of correlations among local occurrences. What causal information adds to this information that we can get just from the dynamical laws and probability distribution, what it adds to information about the pattern of correlations, intuitively, is a separation of information a parameter carries in virtue of being correlated with past events from information it carries, in virtue of being correlated with past events from its own effects. So it separates the effects of a parameter from the information that a parameter happens to carry in virtue of having the same past causes as future events. So according to interventionists, the additional information tells us what would happen. What would happen if we could interrupt the orderly dynamical flow and twiddle or tweak or change the value of the variable. It tells us what the effects of variation in A, where A is some parameter, would have if it could be, as it were, lifted out of the dynamical flow, severed from its own past causes, and allowed to vary freely. This lifting of a parameter out of the dynamical flow and treating it as a free variable is what is meant by an intervention. Information about the causal effects of A, according to interventionists, is information about the results of hypothetical interventions. It tells us how future probabilities would be affected by variation in A when A is treated as a free variable. So even though there may be a strong law-like correlation between having breath that smells like cigarettes and developing cancer, bad breath is not regarded as the cause of cancer because the cancer rate would not be altered by giving people mints to improve their breath. Smoking, by contrast, is regarded as a cause of cancer because abolishing smoking, it is believed, would significantly lower the cancer rates. That's what it means to say that bad breath is not, but smoking is a cause of cancer. For any set of dynamic equations of sufficient complexity, we know that there will be multiple conflicting causal models that satisfy the equation. These models will preserve the network of probabilistic correlations entailed by the laws, but disagree over the results of hypothetical intervention. Causal structure separates what a parameter does, again the effects that it brings about, from the information it happens to carry about the future in virtue of common causes in the past. Since that's a difference that only shows up when its own links to other variables are severed, and since no variable is ever actually severed from its own causes, this extra content can be captured only in counterfactual or subjunctive terms. Think of a newscast in which Obama announcing new measures in Afghanistan follows a weatherman forecasting the rain. Now, firing the weatherman won't ward off rain, but firing Obama would ward off the announced measures in Afghanistan. But that difference, the difference between Obama's connection to the events he announces and the weatherman's connections to the weather, is not one that can be made just in terms of correlations between the reports and the events reported. And that's what it means to say that Obama's announcement actually causes or brings about the events that he's reporting. Now, there are various ways of effectively severing the links to the environment when attention is focused on a prescribed system in the laboratory or in real life, so that we can treat changes in the values of some variables as interventions. Any variable that can be manipulated and whose own causes are uncorrelated with variables of interest can be regarded for such purposes as external to the system or exogenous, and changes in the value of such variables as interventions. This is the essence of scientific experimentation.